what might be beating a dead horse, but just so that we're totally clear about what it means to differentiate a function with respect to a particular variable, and in particular what that looks like using the usual Newton notation with a prime versus the Leibniz notation with a ddx, since both of them will be important in what follows. And then after that we'll talk more about extracting more data from an equation by differentiating both sides. We've done some of that already, but it's a very common technique to differentiate both sides of an equation. So this is sometimes called implicit differentiation, as we'll see. So I'd like to see more examples of that. But okay, first the notation and beating a dead horse. So what do I mean by clarifying our notation for the derivative? So I think we alluded to this slightly, but just to be totally explicit about what we're talking about here. So when we have a function f, we think of that as a set of ordered pairs, but often we express it as a formula in terms of a dummy variable x, as you know. So if we've done that and expressed the formula in terms of a dummy variable x, then we can write this expression for the difference quotient, which defines the derivative of f at a fixed real number a. So now a is something handed to us. We're asked to compute the derivative at that point a. And it has this expression in terms of the limit as h goes to 0 of f of a plus h minus f of a over h. Now it's important here that we know that we're using, I guess, x. If you have an explicit formula for f, it's important when you look at that formula to know that f is the dummy variable. Why is that important? Because to evaluate this limit, this difference quotient, what you would do operationally is look at that formula for f of x. Everywhere you see the dummy variable x, you would plug in a plus h in this first term, and then you would subtract what you would get by plugging in simply a for x again in the second term. So it's very important that we are substituting in for this dummy variable x, right? When we compute this limit, only the variable x is changing between these terms. So if f depends on some other numbers, like maybe you put a b or a c, some constants in, those things do not change between these two terms. You plug in a plus h for x, you plug in a for x, any other numbers which appear in that function do not change between those terms. So the words we use to describe this are differentiating with respect to x. The words with respect to simply mean that the thing which is changing between the terms in the difference quotient is the dummy variable x alone. So differentiating with respect to x, for instance, is different, it's not the same, as differentiating, say, with respect to b, if there's another number b which appears in this function f of x. Because differentiating with respect to b would mean instead of plugging in a plus h for x, you would plug in a plus h for b, and then plug in a for b, and it would give you a completely different answer. So one should be very careful about whether the formula you've written down is a function of a dummy variable x with b constant, or a function of a dummy variable b with x constant, because those are entirely different. And I have a large number of examples to follow in the next couple slides that will emphasize this difference. But before that, thoughts on this distinction?
I do not have any thought.
Okay. Well, all right, I will do an example and then challenge you to do some on your own. So here's an example. To be totally explicit, we're going to have a function f, the dummy variable is x. There is now a constant a, so a is some fixed real number, which I've said here, a is in the reals. And then we're also going to fix a second real number b, which is the point at which we're going to evaluate the derivative. So this is a function of a variable x, and we're asked to find the derivative at a particular point b. And we're asked to find that f prime of b in terms of g prime of b. So we should be careful. I mean, we know how to apply the derivative rules to this function, but you have to be careful about when you chain rule what gets differentiated on the inside. So here's the solution. As requested, we're going to find the derivative of f, this function, at the point b. So we use the chain rule. We take the derivative of the outside function with respect to its argument, the inside. So this is g prime, and then the inside is left alone. The inside is left alone, which means That's x plus g of a, where g of a is a constant. But since we're differentiating and finding the slope of the tangent line at the point b, this x is replaced by b. So that's the first step in the chain rule. Derivative of the outside with the inside left alone, and we're evaluating at the point b. Then we would usually multiply by the derivative of the inside. The derivative of the inside, well, the derivative of x with respect to x is 1. The derivative of g of a with respect to x is 0. This is the key step. It's extremely important that this is obvious to you. If I say this and you are not angry with me for saying something so obvious, then we should talk more about it, because this function, this thing inside the parentheses does not depend on x at all. When I compute the difference quotient, where I take, this is going to be very stupid notation, when I take g of a and then I plug in x goes to b plus h, and then I subtract that number g of a, where I plug in x goes to b, this is 0, because the statement that you take the number g of a, which is simply the number you get by plugging in the constant a into the function g, that just gives you a number. It has nothing to do with x. This is just a number like 11. If I take 11 and replace x with b plus h, well, there's no x, so it's still 11. If I take g of a and replace x with b, again, there's no x, so it's still 11. So the numerator of the difference quotient is identically 0, which means the derivative with respect to x of g of a is necessarily 0. So in particular, we should not think this is not the same as anything depending on g prime. I don't know, g prime of a or g prime of x or something. There's no x in sight. So this is the dead horse I'm beating on this slide, that even though a g of a appears inside, its derivative is 0. So this is the correct expression for f prime at b. Okay. Questions, thoughts?
Were there further thoughts to why there is a not equal to g prime of ...
Further thoughts as in, like what, like an explicit thing that ... would have been that I thought you would be confused about? Or are you asking for more explanation for why this is not equal to anything involving a g prime? Or neither of those things?
Say that again?
So are you asking, when you said, are there more thoughts about why this is not equal to g prime? Are you asking for more detail on why this thing is 0 and not something involving g prime? Or unpack the question is what I'm asking you to do.
Now I understand.
Oh, you do understand. Okay. So you are happy with this statement, that ddx of g of a is 0 and is not something involving g prime. You're happy with this statement.
So it would seem that now you're telling me that a is not a dummy or replacement for x?
Yeah, I even said that in the problem statement, right? So I said fix a and b in the reals. So when
I'm talking like in the past.
Oh, well, I mean, a is just a letter, so in the past depends on when in the past, right? So sometimes in the past, I've used the letter a for the point at which we evaluate the derivative. Sometimes in the past, I've used a as some constant appearing in a function. So, yeah, in the past is context dependent, because in every problem, we'll usually use the letter a in some different way, right?
Okay.
Good. Other questions on this?
I have no question.
Okay. Good. Okay. Let me do one more, and then I'll ask you to do something like this. So here's a similar looking example, which is totally different. So now, instead, we let f of x be g of the quantity x plus g of x. and I copy pasted, so a should not actually appear there because a is not used in this problem. But now we're going to fix again a constant b, which is a real number, and do the same thing. We're asked to find f prime of b in terms of g prime. So now we'll do the same thing. We apply the usual chain rule to differentiate f and get its derivative in terms of the derivative of g. So when we do that again, we take the derivative of the outside function, which is this first term here. This is the derivative of the outside, with the inside left alone. So the derivative of this would be g prime at the point x plus g of x, now evaluated where x is b. So that is g prime at b plus g of b. This is the first factor. The chain rule invites us to multiply by the derivative of the inside. The derivative of the inside with respect to x is 1 plus g prime of x, because now this expression is not a constant. It's not g of a, this is g of x. So we differentiate g of x with respect to x to get g prime of x, now evaluated again at the point b. So this is altogether g prime of b plus g of b times the quantity 1 plus g prime of b. So the kicker is that this is different. This is not the same as what we would have had in the previous slide, which did not have this second term coming from the chain rule, which was just, I think it was something like g prime at b plus g of a or something, right? So this is different because I'm emphasizing the difference between the argument of the function, x, which is hit by all derivatives, and constants like a, which are not hit by derivatives. Their derivatives are constants. Okay. Questions on this thing?
I have no questions.
Cool. Alright. Okay. Now I'll ask you, there are 4 examples that all look relatively similar with some a's and x's. So the setup is the same. A and b are fixed real numbers. They could be, I don't know, 11 and 5 or something. They're just numbers. They have nothing to do with x. And in every one of these 4 examples, we're asked to find f prime in terms of g prime. So you use the usual rules for taking derivatives, but be careful about what is a variable, what is, in other words, the argument of the function, or the thing which is replaced by, say, x plus h and x in the difference quotient. Be careful about what is a variable and what is a constant, like g of a. Okay, so to begin, I will ask you, in the first case, when f of x is g of the quantity x times g of a, what should I write for the derivative of f evaluated at a point b?
This is going to be by the chain rule, but give me a second to think.
Are you whispering because there are people nearby?
No.
Yeah, okay. I thought Mason was in the room again and you were feeling awkward.
Is this going to be g prime of b times g of a? And think about the second.
Okay, so that's the derivative of the outside, correct? And then derivative of the inside with respect to x.
Is this going to be g of a?
Yeah. Since the inside function is just a line with slope g of a, right? This is like mx, where m is g of a. Good. So this is the first bit. Okay, now this thing, which has g of x times the quantity x minus a. So again, what is f prime of b in this case?
So I believe that this is going to be by the product rule.
Yes.
So this is going to be g prime of b times x minus a plus g of b times thinking. This is going to be, times 1 minus a.
Well, it would be times the derivative of this thing, but the derivative of this is 1 minus 0, because the derivative of a is 0, right? So I think it's just g of b times 1, or just g of b. Right.
I understand that.
So the product rule says derivative of the first piece times the second left alone, which is what... Oh, whoops, sorry, this should not be x minus a. I made a mistake in writing this. It should be b minus a. So derivative of the first factor times the second left alone at the point b, as you say, is g prime of b times b minus a. Then we add the derivative of the second factor times the first left alone. So the first left alone, but evaluated at b, is g of b. The derivative of this factor is 1, because the derivative d dx of x minus a is 1. Right?
Is that because both x and a are constants in this case?
No, x is not constant.
To the first power.
Yeah, so this is the power rule for x. So d dx of x is 1. d dx of a, if you prefer ax to the 0, or if you like, d dx of a is 0. Right? So linearity, the derivative is 1 minus 0, which is 1. Good. Okay. Let's do the third one. So
Wait, I need further about why the derivative of a equals 0.
So this is...
Wait, we went over this before.
Yeah, let's make sure we're totally clear on this. So let's do the definition. So I'll make a new function h of x equals a. What is the derivative h prime at a point b? So we should always go back to the definition. If you can't go back to the definition and understand it with the definition, then you're lost. I've already used the letter h, so I'll change it to k. Limit as k goes to 0 of h of b plus k minus h of b all over k. Okay, what's this? That's the limit as k goes to 0. What's h of b plus k? Well, h is the constant function a. So regardless of what the input is, the output is a. What's h of b? Same thing. H is a constant function. It always outputs a. So this is the limit of a minus a. And now my pen's getting in the way. This is the limit of a minus a over k, which is identically 0. So what have we just proven? We've proven that the derivative h prime at any point b equals 0, which means that's the derivative of a. Right? The derivative of a is 0 because a is a constant independent of x. Right? QED. Okay. Is this argument for the proof that the derivative of a constant is 0? Is this all clear?
Okay.
Good. Okay, so I will erase this to make room. Okay, so we're happy that the derivative of a constant is 0, which is the reason why this was g of b times 1 and not 1 minus a. Then let's do the third thing. So this looks very similar, but with g of x replaced by g of a. So what is f prime at a point b for this third function?
Believe that g of a is a constant here.
Mm-hmm.
So we only need to take the derivative of x minus a. So it is overall g of a.
Yeah, exactly. So this is just, again, a slope. This is like f of x equals mx plus b. It just so happens that m is g of a, and b is negative a g of a. But we know that the derivative of a line with slope m is just m. So, good. Alright, tricky part. This is where we have to be careful about what we mean by the dummy variable. So now the dummy variable is not x. The dummy variable is x plus 3. So we are asked to take the derivative with respect to x plus 3. Not the derivative with respect to x, the derivative with respect to x plus 3. Okay, so what should I do to do this derivative?
I don't have any solid thoughts, but it seems like we're just going to have that thinking. It would seem that f prime of b in this case is going to simply be g of x squared.
So we say f prime of b equals, what did you say, g of x squared?
Yes. I'm thinking.
Well, let's see, f prime at b should just be a number, right? Because b is a constant. So this is the slope of a tangent line at its particular point. But g of x squared is a function. So something's wrong with this equation because we've set a constant number on the left equal to a function of x on the right. Something's a little mysterious.
Does it equal 1?
Don't think it should be 1 since g still depends on the dummy variable x plus 3 in some way. If we change this dummy variable x plus 3, then x squared is also going to change in some way, right? So if we change the x on the left side by a little bit, it's also going to change on the right side by a little bit. So the derivative should be non-zero because it's not constant in x, but it's just not going to be quite what we expect. Maybe a hint would be useful if it's usually easier if you can express both sides in terms of the same dummy variable, because we've memorized all these derivative rules which apply to a function expressed in terms of the variable you're differentiating with respect to. So if I express the argument of g in terms of the dummy, well, that's pretty simple. You just say this is x plus 3 minus 3 quantity squared, right? So, I mean, if this is difficult to think about, you could just think of this quantity x plus 3, which is the dummy variable of f. You could think of that as a new variable y, if you like, if that makes your life easier. So we're really saying f of y is the same as g of the quantity y minus 3 all squared, right? So this is the first step to express the functions in terms of the same dummy. Once we've done that, now what should I do to differentiate?
I guess we're going to take the derivative of both sides and let me think. Is b a point we are given?
Yeah, b you can assume is handed to us. So b is a constant, which is fixed, and we know what it is, and it's constant. Sure.
I'm going to throw out words and hope they help. No, I'm not going to do that.
No, you should, though. I was trying to force you to say more of your thoughts so I can hear more and get more of a dialogue.
guess I don't see anything else to do but to take the derivative of both sides and apply the chain rule to the right side.
Okay, good. So let's do that. On the left side, man, my pen just died. Come on. Yes. Okay, so now it's still broken. Well, while I'm trying to fix this, when we take the derivative on the left side and evaluate at the point B, what do I get on the left? Or on the right, either. I mean, whichever you prefer to differentiate. Tell me what one of the sides should be.
Are we going to be taking the composition of functions on both sides?
So not on the left side, because on the left, we're now differentiating with respect to the variable x plus 3. So, I mean, if you want, you could think of this as composing, an outer function f with an inner function x plus 3. But we're being asked to consider this new quantity x plus 3 as the dummy variable, the argument for the left side. So I think the left side, when we would take the derivative, it should just be f prime evaluated at the point B. So f prime of B, once my pen starts...
I like how I've been thinking about that for how long, and I'm like, no. How can we... Are we choosing x such that it satisfies that it equals b?
Yeah, I guess you could think about it that way.
Any sense at all?
Well, yeah, so we know what b is. I don't know if we choose x necessarily. It's where we have a function which is expressed in terms of a dummy, which is written x plus 3. We know how to differentiate that function by using the difference quotient, which means everywhere you see x plus 3, you plug in, say, b plus h, and then everywhere you see x plus 3, you plug in b, and then you take the difference, divide by h, and take the limit as h goes to 0. That's the procedure. So you do that, and that gives you some f prime where x plus 3 equals b. Right, so if you prefer, you can think of that as choosing x so that the sum x plus 3 equals b, which is, I think, what you were suggesting a moment ago. But, I mean, more abstractly, it's just evaluating that limit, right?
So I've had the answer in my mind and just didn't say it.
That's fine.
Okay, so on the left side we have f prime of b, and on the right side we have g prime of b minus 3 squared times, let me think, the right side is weird.
It is.
Is going to be 2 times b minus 3.
Yes. As you say, so the left side is f prime at b. The right side...
Oh, excuse me, b. Still b minus 3. I'm correcting myself when I'm wrong. Right, I don't know.
I think what you said was right? You said g prime at b minus 3 squared times the derivative of the inside, which is twice b minus 3. Right? Isn't that what you said the first time?
Kind of?
Kind of. Well, let's
I may have not heard you right.
I apologize if I misheard. So,
It goes astray.
So, I don't know. What I thought you said was, now that my pen works, differentiate the right side, derivative of the outside is g prime at the inside left alone. So this is b minus 3 quantity squared. Why is it b minus 3? Because this thing, we're setting x plus 3 to be equal to the point b at which we're evaluating. So g prime of b minus 3 quantity squared times the derivative of the inside, which, as you said, was, I think, twice b minus 3. Right.
Yes.
Good. Okay. This is correct. So it's subtle when the expression inside the function, the argument of the function, is not just x. If it's something more complicated, we have to be careful and make sure we express both sides in terms of that same dummy. So let's check that we didn't make any mistakes. So this is, I believe, what you said a moment ago, g prime of b g of a times the derivative of the inside, which is g of a. In this one, we use the product rule, as you said, so g prime at b times the second left alone, b minus a, plus g of b, because the derivative of a is 0. In this one, as you said, this is just a line with slope g of a. So this one is constant, it's constant derivative. And then this one was tricky. We re-expressed f of x plus 3 equals g of the quantity x plus 3 minus 3 squared, differentiated with respect to x plus 3. So f prime at b, which means x plus 3 equals b, is g prime of this whole thing is b, so g prime of b minus 3 squared times twice b minus 3. Good. Okay. Thoughts on these examples?
So this was basically an exercise in saying that when you substitute something, you need to substitute it everywhere.
Yes, true. This is, for instance, the same reason why ddx of sine squared x is not what you would just get by pretending that this thing is some x squared, right, of twice sine x, because you could think of this, if you prefer, as being a derivative with respect to a different dummy variable. If you had said that my dummy variable is now sine x, then it would have been true that this is twice sine x, for the same reason that if your dummy variable is x plus 3, you express everything in terms of that dummy and differentiate with respect to what comes inside the function. Right? So if this were inside the f, if it were sine x, then I would differentiate with respect to sine x and treat that as my variable. So if I were treating sine x as my variable, then this would be twice sine x. If I were treating x as my variable, then this is very different. This means replace x by, say, a plus h in the difference quotient, which requires the chain rule. To fix this, you would need derivative of the inside, is the point. But yeah, this is, as you say, it's about being careful to make sure on both sides of your equation that your substitution of an expression for the dummy is applied everywhere democratically. Good. Other comments?
I have no other comments.
Good, because we have more of these. Okay, well first, before doing more, I will emphasize the punchline so that we do not confuse different types of symbols. So the first type of symbol, as I've emphasized, is the independent variable, or the dummy variable in your function definition. So the first type of symbol in any derivative calculation is the thing you are taking the derivative with respect to. So for instance, if you take f prime of x, you are differentiating with respect to the independent variable x. Good. That's the first kind. The second kind is a constant, so you say fix, for instance, some a in the reals, and then put that constant in the definition of your function, but because it is fixed, it does not depend on x. So this is like the a in that g of a example. This a, the derivative of this a is 0, because it's a constant. This is the second kind of symbol that will appear. And then the third, this is why I've been very explicit about computing the derivative at some point b, right? This is the point at which you evaluate the derivative or find the slope of the tangent line, say some point b in the reals. So that's when you take the derivative, the number which is being substituted for your dummy, x. So it's worth being very explicit about this because, strictly speaking, when you take a derivative, you are evaluating it at a particular point. So it's usually clearest if you make that point totally explicit by giving it a name. But as you've seen, often we skip this step and just say we take the derivative at some point b, and then you say, well, I could have done this at any point b whatsoever, so I simply replace b by the same dummy variable x as appears in 1, and think of this as a new function. Right? This is what we do, for instance, when we say the derivative of sine x is cosine of x. Right? So we should be totally clear about this step that we're skipping here. We're saying that at any real number, at any point, say b, I know how to take the difference quotient, the sine of b plus h minus sine of b all over h, take the limit. I know how to do that, at any b. And since I can do it at any b, I might as well call the point at which I do this, instead of b, I can call this x, and think of this as a machine that takes in a number x, computes this, where I replace b by x, and then spits out the slope of the tangent line. But if you, as long as you understand the skipped step, it's fine to do this and just write d dx of sine x equals cosine x, because, I mean, once you've done it enough times, it's clear what's going on under the hood. But it should be clear when you're doing this that there's really an implicit, implicit substitution going on secretly, because the procedure of computing the derivative at a particular point depends on the value of that point, right? So we're kind of being sneaky and using x both as the dummy for the function and the dummy for its derivative. So it's totally fine. Just do not become confused by it, since it's very common to skip this step. Okay, thoughts here?
I do not have any thoughts.
Cool. Alright, more examples like this. This was the slide that I asked whether I should delete, but I did not delete. So, 3 cases. These functions all look the same. F of x equals ax squared, g of x equals ax squared, L of a equals ax squared. The right sides all look the same. The derivatives in these 3 cases are all different. Why is that? In the first case, I say I hand you a number a, and then compute f prime of x, right? What do I mean by f prime of x? I mean compute f prime at some other point b, and then replace that b by the same dummy x, which we are using in the function definition. This is the skipping the step I just mentioned. So if we do that, by the definition, this means take the limit as h goes to 0 of this function, ax squared, where x is replaced by x plus h. Right, that's the confusing step. There's an interim. We're replacing x by x plus h. Do that, subtract the function with x replaced by x, divide by h, take the limit. We've done this calculation many times. It's twice ax. So that's fine. This is the normal thing you would do just by looking at this and blindly applying the power rule, right? The derivative of f of x is f prime of x equals 2ax. Fine. That's one thing. Second thing, still fix the constant a. I use a different letter so we don't get confused, but call it g of x. It's the same as f. It's ax squared. The difference is now I'm asking you to compute g prime of a. Now the thing that is confusing about this is because I'm using the letter a both for the constant appearing in the function, which was variable type 2 on the previous slide in the 3 types of variables. It's being used both as the second type of variable and as the point at which we evaluate the derivative, which was the 3rd type of variable. Right, so this symbol a is appearing both as a constant in the function definition and as the place at which we evaluate the limit. What does that do? Well, that means, again, by the definition of the limit, I'm computing g prime of a. So I replace everywhere I see an x in this definition by a plus h, subtract what I get by replacing it with an a. Now this looks very similar to the previous one. I square this, get like an a squared plus 2ah plus h squared. The a times the a squared gives me an a cubed, which cancels this a cubed, blah, blah, blah. Now I get a different answer. This cannot depend on x. The left side has nothing to do with x, so the right side is better have nothing to do with x as well. And in fact, this is precisely what we would have gotten just by taking our result for f prime and plugging in a. So that's fine. But we should be clear about what steps went into this, right? Same function, evaluated at a particular point. Now the most interesting contrast is example 3, where now instead of saying fix a constant a, now we say something else, fix a constant x. So now x is in the reals, x is a constant, x doesn't change. For this function, L is a machine which takes in a dummy a and spits out a number. So now a is the variable, x is the constant. What's L prime of a? Well, now we have to be careful. We still use the definition of the derivative, but now since L is a function of a, in this definition we replace a by a plus h and a by a in the difference quotient and subtract. And as expected, since as a function of a, this is just a line, right? This is just a line with slope x squared, since a is the variable. As expected, we get the derivative, which is that constant slope, x squared. So just to drive home the point, in example 1, we are, well, also in example 2, but here we differentiate with respect to x. By this I mean x is the dummy variable in the function to which we apply the derivative rules. In example 3, we are differentiating with respect to a. Here a varies and x is a constant. So this is why the answers are very different. Good. Thoughts here?
I do not have any thoughts.
Sweet. Okay, I think more challenges for you next. Ah, good. I like this. Okay. This is actually a problem straight out of Spivak, and I quote Spivak on the next slide. But okay. F of x equals x cubed. What are these three numbers? F prime of 4, F prime of 9, and F prime of 16.
Are they all 1?
No.
Okay.
Why did you think all 1? What was the reason for this?
I was thinking, because we're substituting x4 and 4 to the power, I don't know, 4 to the power of 3 is 12. Derivative of a constant is, wait, 0. Why did I say, I don't know.
Well, it's also not 0, right? We spoke about this thing before, about,
right.
Say, if f of x equals x cubed, you do not first plug in 4 and then take the derivative. If you plug in 4, you get 4 cubed, and you take the derivative, you get 0. The notation f prime of 4 means take the derivative with respect to x and then plug in 4, right? So 3 times 4 squared. So the notation f prime at 4 means take the derivative and evaluate that at 4. Right.
So 3x to the power of 2 in our first case.
Equals 3x2. Okay, so then, good. So then what are these things?
48.
Yeah, so this is what, 3 times 16, or 48. I don't know why I'm writing that. 48. You don't have to actually do the arithmetic if you don't want. You can leave it as a product of numbers, but okay, what's this?
3 times 9 cubed. Wait, no. Why did I say that? 3 times 9 squared.
Good.
Be super lazy.
And f prime at 16.
3 times 256.
Good. You know 16 squared, or 2 to the 8th, which is 256. Okay, now a contrast. What are f prime at 2 squared, 3 squared, and 4 squared?
So I believe we have that f prime of 2 to the power of 2 is going to be 3 times 2 to the power of 2 to the power of 2, which is going to be 2 to the power of 4.
Yeah, so 3 times 2 to the 4.
Yeah, 3 times 2.
Which is again 48. Good. What's f prime at 3 squared?
3 times 3 to the power of 4.
Yeah. 3 to the power 4 is again 9 to the power 2. What's f prime at 4 squared?
3 times 4 to the power of 4.
Yeah, so 3 times 4 to the 4, which is again 3 times 16 squared. Right. So these are actually precisely the same. Why? Because the examples in the first line, 4 is the same as 2 squared, 9 is the same as 3 squared, 16 is the same as 4 squared. So we evaluated the derivative at the same numbers. Right? 4 is the same as 2 squared. So let's just generalize this. What are the expressions f prime evaluated at a squared and f prime evaluated at x squared? What are the expressions for these?
We have that f prime of a squared equals 3 times a to the power of 4.
Good. And f prime of x squared.
I'm scared by this one, but I'm gonna say what I think it should. Is this going to be 3 times x to the power 4?
Yes. Good. Yeah, the point of all of these calculations is that the notation f prime of some number simply means take this derivative function and everywhere you see x, replace whatever this number is. So even though this thing involves x, or x squared, for instance, the notation f prime at x squared simply means take the function for f prime, everywhere you see an x squared, an x, replace an x squared. So indeed, as you say, this is 3x to the 4th. Right, so at this point you may be thinking this is a very silly example, and if so, then Spivak, well, these are the solutions, but I mean the same as what you just said, so I won't go through them. Spivak says, after giving this problem, that if you do not find this problem silly, then you're missing a very important point. Right? As I've said, f prime at x squared means the derivative of f evaluated at a particular number, and it just so happens that we are calling that number x squared. It's not the derivative of x, derivative at the point x of a different function, g of x equals f of x squared. So then he says, just to drive the point home, and gives you another problem. But just to translate this paragraph for you, what Spivak is saying is that f prime at x squared is absolutely not the same as f of x squared prime. Right? He's saying f prime of x squared is the derivative of f at the number x squared. It's not the derivative of this other function, f of x squared. So it's not prime of f of x squared. So let's see that explicitly to drive the point home, as he says. So same function, f of x equals x cubed. I'll copy the answer you gave me a moment ago. So you told me that f prime at x squared is 3x to the 4th, right? So now, what is f of x squared quantity prime, or just to use a little cleaner notation so we don't get confused, what is the derivative g prime of x, where g of x is the function inside the parentheses here, f of x squared. So what is g prime of x?
So I believe that we can turn this into a composition of functions where our outer function is f and inner is x squared.
Good. Then what do we get?
F prime of x squared times 2x.
Mm-hmm. And then what's f prime of x squared? We have a formula for that.
That is 3x to the power 4.
Good. 3x to the power 4 times 2x, which if I can do algebra is 6x to the 5th.
Oh.
Good. So as Spivak alluded to, these are not the same. Priming the outside is not the same, or priming just f is not the same as priming the outside if x appears inside the argument, right? So here's that again. Again, f prime of x squared, as you told me, is 3x to the 4th. G prime, by the chain rule, you also said f prime of x squared times 2x, which is the 6x to the 5th. So f prime of x squared is not the same as f of x squared quantity prime, is the takeaway. Okay, thoughts on this?
I have no thought.
Good. Alright, more with this x plus 3 business. Okay, so first one. F of x equals x plus 3 raised to the power 5. So for each of these three cases, we're asked to find both f prime of x and f prime of x plus 3. So in the first case, what is f prime of x?
For whatever reason, I feel weird about how the prime is placed in that. I don't know.
About the way I drew it, you mean?
Yeah.
Oh, okay. I'll rewrite it and try to place the prime in a better place. How about f prime? Is that?
Oh no, I don't know what I'm saying. Are we still able to place a prime over the entire right side?
You mean like this? Like that?
Yes.
Yeah, I mean, this notation isn't used that much, but it's, I think, technically correct, right, to put a prime around the whole right side if you remember that this means prime with respect to x. So, yeah, that's fine. But anyway, so this should be automatic. What does this evaluate to?
That's me missing the button. We're just substituting x for x here, so it seems reasonable to say that. Let me think. I believe we can apply the chain rule here.
Good. And what do we get?
So 5 times x plus 3 to the power of 4 times... Still thinking. I believe that this is going to be 1.
Yeah, derivative of the inside is 1, so that's it. Good, okay. So then, again, in case 1, what is f prime at x plus 3?
So then we have that, let me think, equals 5 times x plus 6 to the power of 4 times... Still times 1.
Yeah, we don't actually have to take the derivative again, because, I mean, comparing the left side to the right side, all this means is take x where it appears in this formula on the left and replace x plus 3, right? So as you say, x plus 6 now to the power of 4. Good, okay, different case. Now the dummy variable is x plus 3. F of x plus 3 is x to the 5th. What is f prime of x now? If you like, I can do the first step again and express this as f of the dummy x plus 3 equals the dummy x plus 3, again minus 3 to the power of 5.
There I go missing the button again.
Push to talk.
So we have our inner function to do. Actually, I don't believe that we need to apply the chain rule here, so we have f prime of x equals 4x to the power of 5. Yeah, English. 5x to the power of 4.
Equals 5.
Right.
I think it should be 5x minus 3 to the power of 4.
Okay.
Right. So we took the derivative of both sides with respect to x plus 3. So on the left side, took the derivative with respect to x plus 3. That gave me f prime, plug in x for x plus 3. On the right side again...
So we are substituting x for x minus 3.
You mean in going from here to here, you substituted by x minus 3?
I believe so.
Yeah, true. But, I mean, you should understand why that comes out, though, right? So, we're not memorizing the algorithm of replacing x by x minus 3. We should be able to understand why we're differentiating with respect to the quantity x plus 3, right? So, that's f prime of x. What is f prime of x plus 3?
I believe that this is simply 5x to the power of 4.
5x to the power of 4. So let's see, we again differentiated f prime of x plus 3 would be, yeah, in this case it would be f prime of x plus 3 is 5 times x plus 3 minus 3 to the 4, and then x plus 3 minus 3 is simply x. Good. Okay, one more. So in this case, the dummy is again x plus 3. So this is f of x plus 3 is the variable x plus 3 plus 2 raised to the power 3. So we're asked to get f prime of x and f prime of x plus 3. What are these guys?
So we first have that it's going to be equal to x plus 2 to the power of 3, and that is in turn equal to 3 times x plus 2 to the power of 2.
3 times...
Right?
Wait, what, you're telling me the left one? F prime of x?
What?
Which one were you telling me? You're telling me f prime of x?
Yes.
Okay, so you tell me f prime of x is 3 times x plus, what did you say, x plus 2 to the power 2?
Correct.
Okay. Let's see, I think this is right, because we differentiate the right side, get a 3 times x plus 3 plus 2, replace the variable x plus 3 with x, so it is x plus 2 to the power 2, which I think is good. What about f prime of x plus 3?
So our first step is that this is equal to x plus 3 to the power of 3.
Let's see, x
Yeah.
plus 3 to the 3.
No, that's not right. That
Yeah.
would be, yeah, as we were given x plus 5 to the power of 3.
Yeah, I think this one is indeed x plus 5 to the 3, and the intermediate steps are that we differentiate both sides of this first equation. On the left, f prime, where now the prime is taken with respect to x plus 3, f prime of x plus 3 is, from the right side, 3 times the quantity x plus 3 plus 2. And then we simply replace x plus 3 by x plus 3 on both sides, which yields x plus 5 on the right. Good, okay. So the punchline again is these
Wait,
arguments.
do we not need to simplify that? Well, not simplify. Actually, get this.
Sorry. Yeah, I wrote down the function and then didn't take the derivative. Good. 3, thank you. 3x plus 3 to the 5.
I didn't say the derivative either.
Oh,
What I'm doing.
I confused myself. I thought you said 3x plus 3 squared, or sorry, 3x plus 5 squared, but this
I just said x plus 5 cubed.
Oh, so you gave me the original function. Okay, we should differentiate the function. This is the derivative of the function.
Saying as an intermediate step.
Okay, I got confused then.
I got confused as well.
Sweet. Okay, let me unconfuse myself by making sure that what we just said matches what I computed when I did this with a clearer head. So in the first case, I think this is what we had. Yeah, this is f of x, so there's no trickery about the dummy. You just differentiate using the power rule, 5x plus 3 to the 4. In this case, you plug in x plus 3 for x, so it's 5x plus 6 to the power 4. And this one, I think, matches what we had. F of x plus 3 means we can express the right-hand side in terms of the dummy, x plus 3. F prime, with respect to that dummy, is 5 times x plus 3 minus 3. Wow, why did I... made a mistake. This, of course, x plus 3 minus 3 is just x, not x plus 3. So that's what the correct statement should be. And here, f prime of x, this time when you replace x plus 3 by x, inside it is indeed 5x minus 3. So this part's correct. And then for the x plus 5, in this case we again express the results on the right side in terms of the dummy x plus 3, differentiate. If you replace x plus 3 by x plus 3, this is again x plus 5 to the power 4. But if you instead replace x plus 3 with x, it's x plus 2 to the power 4. So this matches what we had. So I think we did everything correctly, modulo the typo in 2. But, okay. Good. More thoughts or questions on the argument of the function?
I do not have any further thoughts or questions.
Good. Okay. All right, let's express some of these results in Leibniz notation. So first, the motivation for Leibniz notation. So again, I'm emphasizing function f. Our dummy variable is x. And in the previous slides, we saw that we can use this to define a new function where there's the skipped intermediate step of computing the derivative at some fixed real number, say b, and then arguing that we can do that for any b and defining a new function whose dummy is also x. Right, so this is the new function, f prime of x. And as you probably inferred, the motivation for Leibniz notation is to interpret this as a sort of, difference in f divided by a difference in x. Right, the numerator is the difference of f of x, where by difference I mean take whatever appears inside the parentheses of difference, plug in x plus h, and then subtract what you get by plugging in x. Right, so of course if you plug in x plus h and x into f of x and difference them, you get the numerator. If you plug in x plus h and x and difference them, you get x plus h minus x, which is h. So you get the denominator. So Leibniz notation is motivated by this, by simply replacing this difference with the letter d and not writing the limit. So the Leibniz notation, as we've seen, f prime of x is written df of x dx, or sometimes this is written as an operator, like a matrix acting on a vector, ddx acting on f of x. Good, so this we've seen, which is all review. Just to emphasize again the notation, since the dummy variable of the function, which we've seen in several examples now, is very important, one should emphasize that Leibniz notation is a bit ambiguous, right? So the notation df of x dx, this is totally unambiguous because we've specified that the dummy of f is x, and that we are differencing and taking a limit with respect to x. So this is totally unambiguous, and it's the same as writing f prime of x. However, by convention, people often write df dx. So strictly speaking, this is ambiguous, because if f were a function of a, for instance, if it were f of a, like in that previous example where we considered ax squared in two different ways, one as a function L of a, and second as a function g of x. So if we thought of f as a function of a, then this notation would be very confusing because, by definition, df dx would be 0, because f depends on a, but not on x. However, if instead we thought of the dummy variable of f as being x, then this notation df dx would be non-zero. So strictly speaking, one should write df of x dx so that we're clear that it's the second of these two possibilities and not the first. But almost no one ever does that. They just assume you will infer by context from the discussion around the introduction of this symbol df dx. You'll infer that, you know, if it's supposed to be non-zero, then the dummy variable is x and not something else like a. So it's implied by context if this thing is supposed to be an f of x, which one should keep in mind. Okay, thoughts on this thing?
So I just had to ask to verify. For example, if we're taking the derivative at a point b, will the x's in the Leibniz notation be substituted for b?
No. If we were taking the derivative at b, you would write df dx bar b. This is the same as f prime of b.
That makes sense.
Yeah, I mean, in Spivak he calls this bar, he calls it, this is a barbaric but unambiguous notation. I love it. It's such a funny way to say it. It is barbaric but unambiguous. Yeah, so the Leibniz notation, the denominator, I shouldn't call it denominator because this is not a fraction. This is not d divided by dx. This is just one symbol taken together, ddx. But the x in ddx never changes to the point at which you are evaluating it. You always write the dummy variable in the lower dx, or dA, or whatever the dummy is. And then you put a bar if you're going to evaluate the dummy somewhere.
Okay.
Good. Other questions on Leibniz?
I do not have any questions.
All right, then I will give some examples of facts in Leibniz notation. So we can convert all of these, which I'll ask you to do more of in the next slide. We can convert all of these Leibniz facts into statements in prime notation. So if I wanted to convert the statement dc dx equals 0 to prime notation, I would say something like if f of x equals c, then f prime of x equals 0, right? So you can see why the Leibniz notation for things like this is a little more economical, because I don't need to name the function. I mean, I guess strictly speaking, I could have written this in the prime notation as c prime equals 0, but that's a little ambiguous, because we're not clear what prime is. If prime means with respect to x, this is 0. If prime means with respect to c, this is 1. So to be totally unambiguous, we should be writing things the way they are in the middle column. But okay, so what does this mean? In Leibniz notation, this is the translation of the statement that if f of x equals ax plus b, then f prime of x equals a, which is what we've proved before. It's this slope stuff. Okay, what's this? The bar, as we've said, means that we're evaluating the derivative at a particular point. So if f of x equals x squared, then f prime evaluated at the point c is twice c. Good. And I won't write them out, but here are some more things like that. The ddx of ax cubed. So again, a is a constant. X is the independent variable, so we apply the power rule, 3ax squared. Same thing we could write in primes. Here's how you express, maybe I'll write this one out just to be totally clear. This one is different because the prime statement would be if f of a is ax cubed, then it's kind of bad 3. Then f prime of a is x cubed. So this is how Leibniz notation tells you what is a dummy and what's a constant. Here a is the dummy, so we apply the power rule, a to the first power, and simply get the slope x cubed. And here's an expression of something, one of these x plus 3 things. So if we were playing one of these games of, f of x is some g of x plus 3, for instance, and evaluating the derivative of f with respect to that translated variable x plus 3, you would express this in Leibniz notation by saying df of x, dx plus 3, say evaluated at b, is f prime evaluated at b minus 3. So this is the same thing we saw before. What you do is you express the inside as x plus 3 minus 3, you differentiate with respect to the plus 3, you replace the x plus 3 with a b, and you're left with the b minus 3. So this is the Leibnizian version of that example. Okay, questions on these barbaric notations?
I have no questions.
Good. Now I will ask you to interpret some specimens of Leibniz notation. So either tell me what the corresponding statement would be in terms of defining functions and writing primes, or else just say some words about what the content of this line is. So the first one says d of c f of x with respect to x is c df dx. So translate or speak about the content of this for me.
I believe that this claim is based off the linearity of derivatives.
Yeah. This is part of linearity. And in particular, the statement is that if g of x is cf of x, then g prime of x is cf prime of x. Good. So that's just a statement that you can multiply by constants. How about this thing?
What is C?
Oh, I guess I should say fix some constant c in the reals. Is your push to talk off, or are you just still thinking?
I am thinking.
Okay.
I don't know if z and y are functions or constants here either.
Yeah, that's the problem with Leibniz notation is you have to kind of guess, right? So we're supposed to infer, looking at this, that z of x and y of x are functions, and that they're two functions such that z of x is y of x plus a constant c. Right, so that's the ambiguity in writing dz dx instead of dz of x dx, but this is how you will see things like this written. So then the statement is simply...
Oh boy.
Yeah, well, sorry. So the translation of this statement then, after writing that, is that z prime of x is y prime of x, which is simply true because d dx of c is 0. Good, okay. Can you explain what's going on in this third line here?
Are these super obvious and I'm not getting them, or am I tired? Wait, was that an or?
I don't know if it's super obvious. Perhaps you are. You do sound a bit tired, or maybe just like, I don't know, bored or something. But yeah, I don't know. If you don't have, if you're not confident in an answer, then just like speak your thoughts, free associate. Like tell me the train of thought as you attempt to answer it.
My first thought was the idea that c divided by x might be equal to 1 somehow, but I don't know if that has any relation or if c over x is actually a fraction.
So c over x, this is actually a ratio of numbers, so this is indeed a fraction. It will not be 1 in general. The key to interpreting this equation is recognizing that the left side is d dx and the right side is d dc. Right? Does that help you in your interpretation at all?
For a few seconds, I thought that Leibniz notation was easy to understand.
Yeah, I mean, it's more compact, so it's easier to write complicated things with Leibniz. So it's easier in that way, but it's I mean, it's like using slang or shorthand or abbreviations, right? It makes life easier for you, but if you don't know the shorthand, it's harder to interpret it until you're fluent in it, basically. So anyway, yes. So noticing that there's a ddx and a ddc, do you have any comments on why this equation might be true?
I do not have any thoughts.
Okay, I will not let you get away with that. You have to say something. Make some observation which has content. Tell me something you are thinking, or if you cannot, explain where precisely you are confused.
I guess this is just an idea. It seemed like the derivative of the left side, well, derivative expressed by the left side, is somehow just a constant times the derivative on the right side.
Yeah, okay. So you say the derivative on the left side is somehow a multiple of the right. Good. The reason why that would be true, and the thing you have to infer, which is not stated here, I'm not actually going to write this in words because I've written it on the next slide, but the point is that on the left side, we are thinking of f of cx as a function of x with c constant, right? So the notation ddx implies that you're supposed to think about x as the variable and c as a constant. So if you think of x as a variable and c as a constant, then the left side by the chain rule would be f prime of cx times the derivative of the inside derivative of the inside, if x is the variable and c is the constant, is just c. Left. There we go. Left. Now the right side, this is the tricky part. Since we've written ddc, the right side is asking us to think differently about f. The right side asks you to think of c as the variable and x as a constant. So I'll ignore this fraction for the moment, but if c is the variable and x is a constant, then this Leibniz derivative is telling us, well, you should take f prime of cx times the derivative of the inside. What's the derivative of the inside? Well, c is the variable and x is a constant. So the derivative of that is simply x. And if you do that, then you see the equation is actually true. These two are equal simply because in this fraction, if x is not 0, I cancel the x's top and bottom, and on the left side I have f prime of cx times c, and on the right side I have f prime of cx also times c. So this equation is true, it's just confusing, because on the left side we're thinking of x as the variable, on the right side we're thinking of c as the variable. Okay. Confusing, but you will, someday when you do physical chemistry and learn thermodynamics, every equation will be of this form where you're taking derivatives with respect to different things on different sides, and it can become very confusing. So we should pause. Questions on this number 3?
I don't have any questions about this number 3.
Okay. Is the argument I just gave about why this thing is actually true convincing to you?
Convincing in the fact that you understand it.
That I understand. Okay, so, but you're unhappy with it's unsatisfying to you, is what you're saying. Or something else.
Okay, now it makes more sense.
Okay. Do you want to ask another question and talk about this more, or are you more happy?
Satisfied.
You are satisfied? Okay. Yeah, I admit it's pretty unsatisfying, just because of the ambiguity, so I apologize for this, but it is one of the things I must prepare you for. Good, okay. This last one, this is very perplexing, but I will again ask you to try to make some statement about it, even though it looks very mysterious. See if you can, figure something out or make some observation.
This is basically identical to effectively canceling out the du.
Yeah, it's very tempting. It's very tempting to
Yeah.
think of these as fractions and say du should cancel.
But they're not.
Yeah, these are just... This is a good mnemonic, by the way. This is a mnemonic to remember a particular result. I'm not telling you which result, but yeah, it's a good mnemonic because your brain wants to think of these as fractions and cancel them, even though they're not fractions. Okay, so what do you think this is actually expressing?
I really don't have any thoughts about this outside of interpreting, like, it might be like some kind of longhand, long-winded way of writing something. I don't know.
Yeah, it's...
Still thinking.
Okay. Yeah, think more and try to make some observation, even if it's just something that you... if you can narrow it down to some subset of derivative rules we've studied and think, well, it can't be this, it might be this. I don't know, some contentful remark.
I'm trying to remember. We could theoretically go backwards in limits and multiply two limits together and get one limit, right?
If both limits exist, then you can take the product of two limits together to one limit of the product. Yeah.
And I believe that dg du represents the derivative that is a limit.
Yeah, okay, so and this is actually some very useful progress. So this is, I'll write out the limit as you say. This is supposed to be, well, we're thinking of g as a function of u, right? So this is supposed to be a limit where we take a difference between these things and then multiply by some other limit, maybe as k goes to 0, of, I don't know, u of x plus k minus u of x over k. Can you think of a proof that we did which involved an argument that we were trying to split a product of limits like this into a limit? Well, we were going in the other direction. We had a limit of a product and we were trying to split it into a product of limits, and we defined a function that involved like this ratio. So there was like the g stuff divided, we called it not u there, but we called it f, remember? So there was a ratio, and we tried to multiply this phi by the f's so we could get a product of the limit of phi and the limit of g. I don't know if this is ringing any bells.
I mean, I remember it, and that's all.
Okay. Do you remember what we were proving?
Remember how we can change that around for what we're looking at right now?
No, so in the proof where we introduced phi, what was the theorem we were proving?
I have no idea.
Ah, so this is proving the chain rule. And indeed, this thing I've written down is a Leibniz notation version of the chain rule. Why is this the chain rule? If, let's see, if we were doing the chain rule for g of f of x, the usual chain rule would say, okay, if you want to take the derivative of this thing, so this prime, you would say g prime of f of x times f prime of x. So in Leibniz notation, it's convenient to define a new variable u, which is f of x, and then the above line would say g of u, since I've replaced f of x with u, g of u quantity prime is g prime of u times u prime. So if u is a function of x, you could rewrite this prime notation statement in a Leibniz notation statement by saying dg dx. This is what I mean by the outer prime on the left side. dg dx is, what's that? Well, it's the derivative of g with respect to u. That's the dg du. You multiply by the derivative of u with respect to x. That's the du dx. So this product of two derivatives is supposed to remind you in the chain rule of the derivative of the outer function with the inside function, which is here called u, left alone, times the derivative of the inside function u with respect to x. Good. So you will often see people write this product of derivatives that looks like it's supposed to cancel, like fractions. They'll write this for the chain rule. Okay, good. I think you made good progress towards that by noting the product of limits thing, since that was the key step of the chain rule proof. Okay. Thoughts on this kind of dubious chain rule notation, or anything else?
No thoughts?
Okay. I think the next slide is just words saying what I just said, but yes. First one, as you told me, is linearity. That this Leibnizian thing means that the derivative of a constant times something, the constant commutes. This thing with z and y is simply the statement that if you have two functions y of x and z of x related by a constant, then the derivatives are the same. This confusing thing meant that, if you wanted to write this less confusingly, you should call these different functions. So on the left side, I'll call this g of x, which is f of cx, to emphasize g of x means that x is the variable and c is a constant. On the right side, it's the other way, so I would write this as h of c, to emphasize that c is the variable and x is the constant. And then the statement here unpacks into the statement that if you fix both c and x and compute the tangent lines of g of x and h of c, then they would be related by g prime of x is this ratio c of x times h prime of c. So this is the more precise way to say this kind of shorthand. And finally, as we saw, this thing is the chain rule. So g of f of x is g of u, where u is f of x, and then we saw the chain rule says the composite, g composite f prime, is g prime at u times u prime of x, which you could write like this. Good, same thing. Okay, I do not think we will get to Act 2 possibly, but okay. Another challenge for you while we are on this. So I have two functions, sine x and x squared, and for each function I would like you to tell me what is f prime of f of x and what is ddx of f of x. Two different things. Okay, so first for sine x. If f of x is sine x, what is f prime of f of x?
So first we have that. I believe that. Let me think. Well, f of x equals sine x, as we said, and f prime of x, or f of x equals sine x. That should be cosine. So I don't know if I have to go any further than cosine of sine of x.
Good, yeah, so yeah, as we emphasized, so f prime is cosine, and then whatever appears in here simply says plug in that expression wherever x appears in the derivative. So cosine of x is replaced to cosine of sine of x. Good. That's the first piece. Now this is different. So just to contrast, this is the derivative composed with f, and this is the derivative of f composed with f. So this will be different. What's ddx of f of x?
I believe that by the chain rule. Let me see. We have that this is going to be equal to negative sine of sine x times cosine x.
So let's see, you say negative sine of sine x. So the derivative of the outside piece sine is cosine, right? Negative sine.
Wait, what did I?
So I think you said negative sine of sine of
wait,
x.
I was basing it off of what we saw before, not realizing that our outside function in the second thing isn't prime.
Ah, yes. Yeah, outside is still f. Good.
So, yeah.
Good, so what should that be?
That is going to be cosine of sine x times cosine x.
Yeah, derivative of outside with inside left alone times derivative of inside. Good, that is correct. And again, of course they differ. Okay, same thing for x squared. So f prime of f of x, hopefully this is knee-jerk for you. What should this be?
Mind if I have a sec to plug my computer in?
Yeah, sure.
I've also turned on the light so I'm not stepping on any dogs.
You were just sitting in the basement in the dark doing calculus?
Oh, right now I'm in the living room.
Ah, okay. I thought you were being a dungeon dweller. Okay. But you were still sitting in the dark, which is kind of amusing.
Yes.
Okay. Good. So f of x is x squared, and now we want f prime of f of x.
So I believe that this is going to be 2 times x squared times 2x.
Let's see. So f prime of x would just be 2x. And then f prime of f of x means replace x by x squared. So I think it should just be f prime of f of x is 2x squared. Right? We're not chain ruling here. We're just taking the derivative and plugging in f of x inside. Right?
What? We aren't chain ruling.
No, it's the same thing.
Oh wait, oh my god, so.
Right. That's the difference, right? The difference is in the left column, there's no chain rule. It's just take the derivative and plug in the inside function. In the right side, we do need to chain rule in the right column.
Okay.
Good. That's the point. Okay, so then what would be, in this case, d dx of f of x?
So before we do anything else, I guess transcribe f of x as x to the power of 2 to the power of 2?
Yeah, so in
Oh.
most countries that's x to the power of 4, right?
Yeah.
Okay. And what's this bad boy?
I believe that is simply 4x to the power of 3.
Good. Okay, so again they disagree, which is what we'd expect. F prime of f of x is not the same as f of x prime. Right? Good, good. Fuck. Good. Okay, well, in principle I should stop talking in 20 minutes, because we will have hit 2 hours, so I will see if we can finish the 7 slides in that interim time. So, I'd like to say a bit more about taking derivatives of equations, right? So we've seen a few examples of this. For instance, in the logarithmic differentiation, as it's sometimes called, we computed the derivative of, say, f of x equals a to the power x by taking a log of both sides, which gave this equation, log f is x log a, and then differentiated both sides of the equation, getting f prime over f on the left and log a on the right. We also did this in that exercise where I said pretend we don't know what the derivative of cosine is, but we know what the derivative of sine is. And then write down sine squared plus cos squared is 1, take the derivative of both sides, chain rule, to get 2 sine x cos x minus 2 sine times this unknown derivative of cosine. And on the right side, the derivative of 1 is 0. And we use that to supply a different proof that cos prime is minus sine. So we've done this before, differentiating equations. It's also useful if you have some curve in the plane, like a circle, a hyperbola or something, and you'd like to find the slope of a tangent line to that curve, but it's either difficult or impossible to actually solve and write that curve as an equation where it's just y as a function of f on the left side equals some junk. Sometimes it's hard to solve an equation for y, so instead of solving for y and then taking the derivative of the right, you would just start with the unsolved equation and differentiate both sides of the unsolved equation, and then solve that new thing for the derivative. So often that's easier. It probably sounded very abstract, the words I just said, so I hasten to supply an example. Consider, for instance, the circle in the plane. So the unit circle with radius 1, and suppose we want to find the slope of the tangent line at this point, which is pi over 4 degrees, so we want the slope of this line here, which just kind of by inspection we expect to have slope minus 1, but calculus should be able to give us that answer. So one way to do this would be to say, well, I know the equation of the circle, it's x squared plus y squared equals 1. That is actually not a function because it fails the vertical line test, but I can slice the graph and just take the top half of the circle, the top half of the semicircle, for instance, and then that would be a function. And what I would do is say, well, I would solve this equation for y. I would have y is plus or minus the square root of 1 minus x squared. This is why it's not a function, by the way, because there's two values, plus and minus. But I say I want the top half, so I take plus. So I take y is plus the square root of 1 minus x squared, and then I would compute dy dx using the chain rule. And this is kind of, I mean, you know, it's not that bad. It's like 1 over 2 square root 1 minus x squared times the derivative of the inside, which is minus 2x, It's not terrible, but it's a little ugly. So you can ask, is there an easier way than solving this equation for y and taking the derivative? Is there something easier? And there is. The easier thing is start with the equation x squared plus y squared equals 1, and instead of solving for y, just take the derivative of each side of the equation, of the left side and the right side, term by term. What does that give us? Well, we're taking the derivative with respect to x, right? So the derivative of x squared with respect to x is 2x. The derivative of y, which we think of as a function, y of x. So now we have to chain rule. Whenever we hit a derivative on y, you have to chain rule, because y is a function of x. So when you differentiate y squared, you get the derivative of the outside, which is 2y, times the derivative of the inside, which is y prime. And then the derivative of 1 is, of course, 0. So then we have this nice equation, 2x plus 2yy prime equals 0. Then you just move 2x to the right, so minus 2x on the right side now, divide by 2y, and then you've solved and gotten that the derivative, y prime, is minus x over y, just by solving this equation. And then if you want the slope at this point, 1 over root 2, 1 over root 2, that's pretty easy. You plug in x equals 1 over root 2, and you also plug in y equals 1 over root 2. So this is, of course, minus 1 over root 2 over 1 over root 2, which is minus 1. And this confirms what we expected by looking at the graph, right? We expected this to have slope minus 1, and it involved much less work than this other approach where you solved and then had these square roots and this ugly stuff. Okay. So is this calculation sensible, or are there questions?
Yes, and for the latter question, no.
Oh, okay. Good. All right. So let me say a few more words about this strategy where you differentiate the equation. But first there's a harder problem. Okay. So I'll ask you to do this. We're going to do the same thing. Here's some ugly curve. X squared plus y is log y squared minus 1. It's really hard to solve this for y. Actually, I think it's transcendental, so you actually can't. So we're going to use the strategy of the previous slide, where you just take the derivative of both sides. So I will ask you to do that, just differentiating term by term. First, what is the derivative of the left side?
The derivative of the left side is the derivative of x squared plus y, which is in turn equal to 2x plus 1.
What's the derivative of y with respect to x?
0.
No. So there was this claim that now we have to think of y as a function of x, and every time a derivative hits y, you have to chain rule and get a y prime, since when we do this strategy, you think of y as a function of x, right? This is what we did with the circle, right? We took the derivative of x squared and got 2x, and you took the derivative of y squared and you got 2y y prime, right? Because y prime is the derivative of y with respect to x. Good. So now back to this case. Then I agree the 2x term, what's the derivative of y with respect to x?
May I quickly comment that it seems like we're using y as both a variable and a function?
Yeah, we absolutely are. That's the confusion about using this strategy, because y is both a coordinate, which labels points in the plane, and when you use this strategy of instead thinking of y as a function, then you need to think of it not just as that point, but you have to think of it as something which depends on x. This is the tricky part of this so-called implicit differentiation. So normally you would want to say dy dx equals 0. Normally you would want to say this because you would say, well, y is some constant, just like dA dx is 0, so this thing should be vanishing. But the trick is that if you think of a curve like the circle, we're going to say, okay, now this is some equation which tells me how to find y given x, right? I plug in some x to this equation, then I could solve that for y. So I'm going to choose to identify y not as a coordinate, but as a function which spits out some y coordinate when I give you the x coordinate. So if you're going to use this strategy, you should be very clear about what you're saying, but the strategy here is to identify y as y of x. So then instead of saying dy dx is 0, we're going to say, well, now to emphasize, this is dy of x dx, which we also can write as y prime of x. Good. So this is part of why I belabored the point about variables and chain rule and stuff like that for so long for the first half, because now when we do implicit differentiation, you have to be clear about whether you're thinking about y as a constant or a function, and we're choosing to treat it as a function now, because we can if we want. Okay, good. Back to the task at hand. So with that in mind, the derivative of the left side.
As we said before, this is going to be 2x plus, I guess, y prime of x?
Yeah, so plus y prime of x. Treating it as a function now. The derivative of the right side.
So the... I guess we are going to chain rule here?
Good. So derivative of the outside.
So we are going to have that the derivative of the outside equals 1 over y squared minus 1.
Good. And times the derivative.
Times 2y minus, 2y, yeah, just 2y. Or is that right?
So chain rule the 2y. What's the derivative of y squared with respect to x?
Two y prime of x, or is it?
It's 2y y prime, right? This is d dx of y of x squared, right? So we chain rule. The derivative of the outside with the inside left alone is 2y of x times the derivative of the inside. Derivative of the inside is y prime of x. Right?
Okay.
Good. Alright, so now we can solve, since we are asked to find dy dx, which is the same as y prime. So I will not subject you to the algebra, but what you do is move this thing to the left, move the 2x to the right, so then we have y prime factoring out, y prime times 1 minus 2y over y squared minus 1 equals minus 2x. We can get a common denominator and combine this fraction, so this is 1 is the same as y squared minus 1 over y squared minus 1. So this is y squared minus 1 minus 2y over y squared minus 1 is minus 2x. And then you solve for y prime. So y prime, I'll put the x back in, y prime of x is minus 2x times y squared minus 1 all over y squared minus 1 minus 2y. This is the derivative, y prime of x. Okay, thoughts on this algebra or the y squared stuff?
An even better question. When would you use this derivative?
Oh, like where does this curve appear?
Yes.
It doesn't, I just made it up.
Okay.
This is an exercise, yeah.
I don't know why I asked that either. That makes zero sense. This is, for the most part, insanity.
Yeah, I mean, the strategy of differentiating implicitly defined functions is very common. This particular function, I don't think really ever, well, I could probably cook up an example where for some particular choice of x this would actually appear, but yeah, this was just made up for an exercise. I mean, this is why I think it's how do I say this? When I talk to students and they like, especially high school students that are studying a very basic, like field of mathematics like trig or calculus, and they ask where am I going to use this in real life, I can't help but think the question's a little naive. Like, where am I going to use this calculus in real life? It's kind of like you're teaching someone the alphabet, and they say, where am I going to use J in real life? And you say, okay, well, fine, there's plenty of words that involve the word J, like jeer, so you tell them jeering. This is where you'll use J in real life. And they say, no, I don't want to know about jeering. I just want to know where I'm going to use the letter J in real life. And I'm like, I can't answer that question. J is, you're learning the fucking alphabet. You have to learn all the letters, then you can put them together to use words, and then you'll use those words in real life. It's kind of the same way when someone asks, where am I going to use this calculus in real life? This calculus is not what engineers use. This calculus is the alphabet. And then once you know the alphabet, then you can find pieces that are going to be used in real life, and everyone will be happy. So anyway, that's a long-winded rant to explain why I pick a function which doesn't actually appear in real life, because you could think of this function as an example of this is the letter J. And, someday you'll put this together with other things.
I'm just curious if it had any value to you.
Yeah, not really. I could probably, well, anyway. Good. Apologies that my function is a little arbitrary, but yeah, strategy's the same. So differentiate both sides, solve. I expressed the answer slightly different here because I took the minus sign and moved it inside, but it's algebraically the same. Okay. So just the words. I'm going to put on a slide the words I've been telling you. So an equation like the one I just gave you, which is not solved for y. It's not of the form like y equals f of x, the way we usually write functions of x. But you can think of this as a function because it determines for each x one or more values of y for which the equation is true. Right? So for instance, if I plug in x equals 1, this is 1 squared plus y equals log of y squared minus 1, and then you plug this into your computer because I don't know how to solve this, and you get some number. I don't know why. I have no idea what the number is going to be, so you get some decimal expansion. I don't know, blah, blah, blah. So I have no idea how to solve it, but it's still a function in the sense that it's a table of values. I put in 1, and then I go to the computer and I get some number out, and I put in 2, and I go to the computer and get some number out. So even though it's not written as y equals f of x, it's written as some ugly equation, it still determines some y's given each x. So you can think of this as a function that sends x's to y's. And that's the rationale for implicit differentiation, where we've been treating this as a y of x, and its derivative is y prime, and so forth. So anyway, the words that people will expect you to know if you talk about this is the following, that if you write an expression... Interesting.
Nice.
Why did that just come through now?
I don't know.
Interesting, but okay, so the words people expect you to know are that if you write an equation like this, which can be thought of as giving y as a function of x, but is not written in a way solved for y, an equation of that form which is not solved for y is said to define y implicitly. And that's a typo in terms of x. So an equation solved for y is explicit. An equation not solved for y, like this one, is implicit. And the thing that we just did, where you take an equation not solved for y and differentiate both sides, is called implicit differentiation. So those are the words you need to know. No math. There's no content in this slide. It's just saying words, which has no educational value, but I'm doing it anyway. Okay. Thoughts on the words?
I do not have any thoughts on the word.
Good. You shouldn't, because they are just words. Okay, last example, which I was going to phrase as a challenge, but I will just do for you, because we are running late. So you remember this Lambert W, which you did on consolidation document 1? We can use implicit differentiation to find an expression for its derivative. So what was the definition of the Lambert W, right? What we did was we started with this function f of x, which was x e to the x. And then we argued that this thing is strictly increasing in a particular regime, so it has an inverse, and we called that inverse w. So w is the inverse of f. And by the definition of inverse, if w is the inverse of f, it's supposed to be that if I take f of w of x, I'm supposed to get x back out, because that's what an inverse does for me. But if I just take this w of x and plug it into f, everywhere I see an x up here, I replace it with a w of x. That gives me w of x e to the w of x equals x. Good, so that's the definition. If I want the derivative, I just use implicit differentiation. I take the derivative of both sides of this equation with respect to x. So on the left side, I product rule. I get w prime e to the w plus, when I differentiate the e to the w, this is w times w prime times e to the w. Right? This is the derivative of e to the w is e to the w times w prime. And I'm still multiplying that by the w of x. On the right side, I just have derivative of x with respect to x is 1. On the left side, I factor out the w prime, e to the w plus w e to the w, all equals 1. Then I divide both sides. W prime is 1 over e to the w plus w e to the w. Now I can actually simplify this, because w e to the w by definition is x. Right? This thing is x. So I can just take the w e to the w, which appears in my denominator, and replace it with x using the definition. So that's, fucker. It's the same as 1 over e to the w plus x. Just replacing it with the definition. Okay, so this is kind of nice. I'm slowly working. The reason I'm introducing the Lambert W function is because it appears when you use the Michaelis-Mouton model for enzyme kinetics in biochemistry. So I think probably by the end of chapter 4, I'm slowly working you up to an example where we can do some enzyme kinetics using the Lambert W. So this is kind of a, I don't know, laying the groundwork for that. But anyway, that's for later. Questions on this calculation I just did?
I do not have any questions. Sounds like fun.
Okay. First, though, is it clear why d dx e to the w of x, I want to make sure you understand this step. Can you explain why this is e to the w of x, w prime of x?
Well, I thought I was understanding it. Now I have no idea where that came from.
Well, okay, so if you didn't know the answer, how would you differentiate? How would you take the derivative of e to the w of x? If I hadn't already told you it's this, what would your steps be? Well, it's a composite of functions, right? This is...
Oh my god.
There's an outer function, which is e to the x, and an inner function, which is w. Right? Good. So, can you say the remainder of the words that come after that?
So this is by the chain rule, I am pretty sure.
Good. So chain rule. What's the...
So our outer...
Good.
Our outer function is e to the power of x, and inner function is wx, so we have that the inverse function of, not inverse, the derivative of e to the x is e to the x, so we have e to the power of wx times the derivative of wx, which is times w prime of x.
But I thought you said the derivative of e to the x is e to the x, so why is this e to the w of x instead of e to the x?
Oh boy.
I mean, you're right, I just want to make sure you know why you're right. Why is it e to the w of x?
I don't know.
Okay, so the chain rule says the derivative of f of g of x is f prime of g of x times g prime of x. So importantly, when I take the derivative of the outside function, f prime, I plug in the inside function. I don't plug in f prime of x, I plug in f...
Wait, so
Sorry.
I could have just said to you that's by the chain rule.
Well, I would want you to say more words than that. I'm trying to get you to explain more words, because sometimes you guess and say something, and then I feel like you're afraid to say words that are wrong, because then when I ask you, why do you think that? You like hesitate and get shy or something. Or I don't know, maybe you just, maybe it's not shyness, I don't know what it is. But I feel like you don't say enough words to me, so I wanted to get you to say more about why it is the derivative of the outside with the inside left alone, even though you were correct.
Yeah, I understood that. I just thought I thought you were asking for something about how w of x relates to the taking the derivative with some words to x.
Oh, with respect to x. Yeah. I mean, that's also related. I mean, you could have said those words too, and I would have been happy. Just trying to extract some thoughts from you. Okay, so that is the last example. The final comment is that we could have done this in a different way. Here we differentiated both sides with respect to x and then solved for w prime, which was great. That works. It gives you the right answer. The other thing is we could have used the inverse function rule, because we derived this thing not last time, 2 times ago, that the derivative of the inverse function is given by f prime of f inverse of x, 1 over that. So since this is the inverse of w, we could have also computed the derivative w prime using that formula. So we have 1 over f prime of w of x, and we could get f prime using the product rule, and then we would get this thing. And you can prove that these two expressions are actually exactly the same just by using the definition we to the w is x. So you just plug in x here, and then they agree. So this is just a check. Calculus works. I mean, this is good. If we proved an equation is true, then that should